Hi, complete lesson in gravitational field. See the description of this video. Already have done several videos related to different units. Related to unit 5 already I have done thermodynamics, cosmology, complete lesson in cosmology, complete lesson in thermodynamics, and 3 different lessons which covers the whole portion of the nuclear decay. So the URL or the link for these videos are given in the description of this video. Also by using the playlist of this channel, you can navigate to any video you would like to watch, right? Okay, so in this lesson I'm going to discuss the unit 5 topic, gravitational field. Already cosmology is discussed already, I have done it already. Okay, so first you should know what is gravitational field. Same thing like electric field. Electric field, we define the region where a charge experiences electrostatic force. Here we define region where a mass experiences gravitational force is defined as gravitational field. Region where a mass experiences gravitational force is defined as gravitational field. Okay, so that you know that. Second, next you should know the how to define the strength of the gravitational field, which is called gravitational field strength, and it is denoted by G, symbol G. Comparable analogy you can compare with electric field strength. How do we define the electric field strength? The electrostatic force per positive coulomb charge. Electrostatic force per positive coulomb charge is defined as the electric field strength at a point, but here we don't have positive mass or negative mass, so here we define the gravitational field strength as gravitational force per unit mass. Gravitational force per unit mass is defined as gravitational field strength at a point. But normally here the point masses we don't consider. I'll come to that point later. But here the gravitational field strength is defined as gravitational force per unit mass, means we are divided by mass. So the notation symbol G, gravitational force F, mass M. So F equal mg, the first equation. The unit of gravitational field strength, the unit of G will be unit of force, which is Newton, mass per kilogram. If you want, you can give it in SI unit, we give it, base units. Newton means, I call Newton's second law, F equal ma. Okay, so Newton means F equal ma, so Newton means kilogram meter second minus 2 per kilogram. You will get meter per second square. Okay, this gives an important conclusion, or it gives a new idea. That means gravitational field strength, the unit is same as meter per second square, which is the unit of acceleration. Okay, so now we are going to compare the gravitational field strength and acceleration of free fall. Normally, you know, the questions related to gravitational field, we don't consider a point mass, or we don't say, normally the past years you can say object A exerts gravitational force on object B. We don't consider, because gravitational force is weaker, much weaker, because there we are going to get an equation, you already would have done it, F equal G m1 m2 r squared, where G is a very small numerical constant. So normally when we consider gravitational force, there should be between two objects, one of the objects must be a planet or a moon or a galaxy or a star. The other one could be anything, even a pen, doesn't matter. But one of the objects must be massive, something like a planet or moon or star or a galaxy, like that, because to exert a significant gravitational force, one of the objects should be massive, the other one could be lighter, no problem. So there we normally consider the gravitational field or gravitational field strength created by a planet or moon or star or a galaxy. So there we can compare the acceleration of free fall of an object towards the planet, or acceleration of free fall of an object towards the star, or acceleration of free fall of an object towards a moon, or acceleration of free fall towards a galaxy, but not much applications. We are going to compare the acceleration of free fall and the gravitational field strength. Are they same or different? We'll get both are the same. I'll show that now. Okay, so already we got an equation that is from the definition of gravitational field strength, which is F equal mg. Already we got the equation. F equal mg is the first equation. Now G we defined as gravitational field strength, which is equal to gravitational force per unit mass. So, and when we found the base unit of G, we got meter per second squared, which is the unit of acceleration. So now we are going to compare the gravitational field strength and acceleration of free fall of an object towards a planet. Are they same or different? Okay, I told that the questions related to gravitational field strength in this topic, there will be a planet or moon or star or galaxy. The other one could be an object. So normally we consider the gravitational field strength of a planet at a distance, or gravitational field strength of a moon at a particular distance, like that. We don't consider gravitational field strength created by a pen at a distance, gravitational field strength created by a cricket ball at a distance. No, we don't consider those things because they are much weaker, right? We'll come to that point. Okay, now we'll consider whether they are same. So for that we'll consider a planet or moon or galaxy, whatever it is. Its mass, let it be capital M. So in this topic, remember that always the distances are measured from the center of mass to center of mass. In electric field, point charges, we don't consider the dimension of a point charge. So there's no problem when we use the equation F equal kq1 q2 r squared, or E equal kq over r squared. R is always measured from the point charge. Point charge means it which has no dimension. But when we consider a uniformly charged sphere, there I told we assume the whole charge is concentrated at the center. This is all about unit 4 electric field. It's comparable analogy. We can compare the most of the equations in electric field and the gravitational field. But here all the distances, whenever there is a question related to distance, any equation, but we are going to get those all equations whenever there is a distance in the equation. Those distances are always measured from the center of mass. Okay, so here there's a planet, its mass, planet or moon or star, whatever it is, its mass is capital M. Okay, so the gravitational field strength of this particular planet at point P, let it be G. That means if I keep an object, now I can say object, one of the, we are going to learn Newton's law of gravitation, where we'll get an equation for the force between two masses. One mass should be related to a massive object like planet or moon or something like that. Other one could be a small object, no problem. Okay, so here's a massive object which is a planet. There's a small object which has mass m, and the gravitational field strength of this planet at point P is G, and at that point the mass m is kept, means the gravitational force is always attractive. So the gravitational force acting on this mass according to this definition F equal mg. So according to the definition of gravitational field strength, the gravitational force exerted on the point, a small mass kept at point P. At point P, the gravitational field strength of this planet is G. So the gravitational force acting on the mass m at point P according to this definition is F equal mg. Let it be first equation, right? Now we'll think about Newton's second law. You know, the object which has mass m has only unbalanced force. We'll neglect all the drag force, nothing is there, no drag force. So the only force acting on the object is the gravitational force F. So the object has an unbalanced force towards the planet. So if I use the Newton's second law now, F equal ma, if I use Newton's second law, the only force acting on the object is F, and its mass is m. The acceleration of free fall is a. Second equation. where A is the acceleration of free fall. Here G is the gravitational field strength. So I got the first equation by using the definition of the gravitational field strength. Second equation I am getting by using Newton's second law, completely different laws. This is the definition of G. This is the Newton's second law. Now compare the forces. The object has only one force, which is F, that is the gravitational force. So the force acting on an object is the same force. So the left hand side is the same. Therefore right hand side should be the same. So that means MA equal to mg, where A is the acceleration of free fall, G is the gravitational field strength. So m and m get cancelled. A is equal to G. That means the acceleration of free fall of an object towards a planet is equal to the gravitational field strength of the planet at that point. Again I am saying the acceleration of free fall of an object towards a planet at a point is same as or equal to the gravitational field strength of the planet at that point. So this idea we don't have in electric field, but here it's a new concept. So A is equal to G, acceleration of free fall, and the gravitational field strength of a planet or moon at a point is the same. They are the same. You must know this, it's not a derivation, but you should be able to show both are the same. I think once this question came in the Edexcel IAL past paper. Okay, so there are two objects, okay, planet and object or whatever it is, with different masses m1, m2. Their center of masses are O1 and O2 respectively, and the distance between the two center of masses is r. So this is, you know, the gravitational force is always attractive. So Newton's law of gravitation. Several times the past they asked to state the Newton's law of gravitation. So the answer should be like this: gravitational force is always attractive, and this force is directly proportional to each mass and inversely proportional to square of the distance between the two center of masses. Okay, that's a Newton's law of gravitation. So F proportional to m1, same thing like Coulomb's law, what we do for the Coulomb's law between 2 point charges. Same similar equation will get it. F proportional to m1, there q1 we put here m1. F proportional to m2, inversely proportional to r square. So when I combine all these, proportional to m1 m2 over r square. So there must be a constant, that is F equal G. The constant is called universal gravitational constant. F equal G m1 m2 over r square. You can compare this with G, F equal K q1 q2 r square, but we used in electric field in unit 4. Same similar type, F equal G m1 m2 r square, where m1 m2 must be in kilogram, r must be in meter. So G is called universal gravitational constant. So the value of G normally given in the data sheet 6.67 10 to the power minus 11. That's the reason I told the gravitational force between normally between two objects very small, because the G value, the index is very small. So if G equals 6.61 10 to the power minus 11 Newton meter squared kilogram minus 2. They are in the Coulomb's constant, Newton meter squared, Coulomb minus 2, here kilogram minus 2. Easy to remember. So remember, where r is the distance between the two center of masses. Okay, so we are going to get an equation for the gravitational field strength created by a gravitational field strength of mass m. So the mass m is a massive mass at a distance r from the center of mass of this object. So this object or planet or whatever it is, it has a mass capital M. What will be the gravitational field strength of this mass, capital M, at a distance r from it, from the center of mass? So at a distance r, we imagine a point P, and at that point a mass, a small mass M is kept. Okay, so the only force acting on the mass M, the small m, which is at point P, we are going to find the equation for the gravitational field strength at point P. So the gravitational force acting on the mass M is given by F equal G m over r squared, according to the definition of gravitational field, according to the Newton's law of gravitation. But we know that gravitational field strength means gravitational force per unit mass. So the gravitational field strength at point P, so gravitational field strength G at point P, that is G is equal, G means gravitational fields, I shortly wrote gravitational fields, I would have written it in words, but I just put it in short, a symbol. G at point P is given by G is equal to gravitational force per unit mass. So we know that the gravitational force acting on mass M is F equal G m1 m over r squared. So the gravitational field strength means force per unit mass. I need to divide this one by the mass of the object which is kept at point P. So that is G m over r squared divided by m. So what will happen? M will get cancelled, Gm over r squared. So G equal Gm over r squared is a very important equation in gravitational field. Similar equation we got in electric field, where E is equal to kq over r squared. You can compare the similarities or the same pattern. G equal Gm over r squared. So this one, next equation, G equal Gm over r squared. That means the gravitational field strength of a particular mass, capital M, obeys inverse square law. That means G is constant, M is constant. That means G is inversely proportional to r squared. Okay, so if the radius of this planet or radius of this moon or whatever it is, capital R, then the gravitational field strength on its surface, what will it be? Use the same equation, G equal, the gravitational field strength on the surface, G equal Gm over r squared, where r is the radius of the planet. Normally the planet or moon or a star is spherical shape. So if we want to find the gravitational field strength on the surface of it, or the acceleration of free fall, I can say acceleration of free fall on the surface of it, Gm over r squared, where r is the radius of the planet or moon, whatever we consider, right? So G equal Gm over r squared is a very important. Okay, so if there's a planet of mass m, which normally the planets are spherical shape, and the radius of the planet, if it is capital R, the center of the planet is O, the radius is capital R, then the gravitational field strength on its surface is given by G equal Gm over r squared, and at a distance r from the center of the planet, which is outside the planet at point P, it's given by G equal Gm over r squared, where r is the distance of the point P from the center of the planet. So that obeys inverse square law. If you plot a graph of G against R, and if I start the R from the center of, if I start R from the surface of the planet, then the graph will be like this. So here, this is the gravitational field strength on the surface of the planet. But if the graph is, if you plot a graph by concerning from the center of the planet, so this is G, 0, and this is R from the center of the planet until the radius of the planet. We will consider that now, but before that, so until the radius of the planet, what could be the gravitational field strength? I'll explain it, but so far no questions based on it. But on the surface of the planet, if the gravitational field strength is G1, like here, beyond it, it will obey inverse square law. So there, if I say this is G, we say the gravitational field strength on the surface of the planet, if it is G naught, or G, will leave it as G. So at distance R1, if it is G1, at distance R2, if it is G2, then G1 R1, so inverse square law is it, so G1 R1 squared equal to G2 R2 squared is equal to, on the surface of planet, GR squared. Okay, because it obeys inverse square law, the multiplication of G into R squared should be the same constant. Okay, so you can ask me what could be the gravitational field strength inside the planet when the distance from the planet, say from the center of the planet, is less than the radius of the planet. Inside the planet, what could be the gravitational field strength? What could be the shape of the graph from 0 to capital R, where capital R is the radius of the, what could be the shape of it? Okay, I can get that, I can derive an equation for that by assuming, by taking the Gauss law, which is not in your syllabus, but as unit 5 A2 exam, it's like university entrance exam, something like that. So they could introduce it and ask to get an expression for the gravitational field strength inside the planet when the radius, when the distance of the point from the center of the planet is less than the radius of the planet. So there we need to use a Gauss law. So the Gauss law says we need to consider where the m is the mass enclosed within the sphere of radius r. So for example, if I want to find the gravitational field strength at a distance r from the center, this is the center r from the center at point P, I should consider the mass enclosed within the sphere of radius symbol r, that is the mass m we should substitute, because outside the planet, when I consider, for example, what I said, G equal Gm over r squared outside the planet, where m is the mass of the planet, I said. Okay, if you consider a sphere of radius symbol r, here this is the r from the center to this point P, where the mass enclosed within the sphere of radius symbol r is the whole mass of the planet. So that's Gauss law is correct if we consider outside the planet. But when we consider inside the planet also, where m must be, the Gauss law says, mass enclosed within the sphere of radius r, where r is the distance at which we are finding the gravitational field strength. So if I want to find the gravitational field strength at a point P which is inside the planet, I should know the distance of point P from the center, which is symbol r. So there I should consider the mass enclosed within the sphere of radius r. Okay, I can find it, but only one assumption I should take: the density of the planet is uniform. If I take that assumption, then I would be able to derive an expression for the gravitational field strength inside the planet. Okay, we'll take the density of the planet is uniform. By using it, we'll find the, by using that assumption, we'll find the mass enclosed within the radius r, where r is the distance from the center of the planet. So m, the mass of the planet, is equal to 4 by 3 pi r cube. That's the volume of the planet into its density rho. So rho is going to be m over 4 by 3 pi r cube. We assume the density is uniform everywhere on this inside the planet. So the mass enclosed within the point P, the spherical shape, is m, that is going to be 4 by 3 pi r cube into the density, volume into density rho. So that is 4 by 3 pi r cube rho. Instead of rho, I can substitute capital M over 4 by 3 pi r cube. You see, now I can use even this one. I don't need to convert this mass. I can use it in terms of density rho, because density is uniform, constant we are taking. Okay, we can use even this equation. So now the gravitational field strength, the same equation, G equal Gm over r squared, Gauss law says where m is the mass enclosed within the sphere. So the gravitational field strength inside the sphere at distance symbol r from the center of the planet at point P, G is equal to G. The mass enclosed is m, which is 4 by 3 pi r cube rho over r squared, the distance of point P from the center of the planet. So here g is constant pi r, so we'll solve it. It will become 4 by 3 pi g rho 4 by 3 pi g rho r cube r squared into r. See, these all constant. 4 by 3 is a number, pi is a constant, g is a constant, rho is a constant. So gravitational field strength inside the planet is directly proportional to the distance from the center of the planet. So now if I plot the graph, gravitational field strength from the center of the planet, how it varies up to the radius of the planet, the graph will be a straight line. So graph will be a straight line because g proportional to r, this is the gravitational field strength on the surface of the planet. Then beyond the surface of the planet, it will obey inverse square law. This would be the graph we should plot. So the variation of gravitational field strength inside the planet is g proportional to r. So nothing new actually. It's only the Gauss law we need to use, and we take an assumption the density of the planet is uniform at all points. So in the exam they might state that and ask you to get an expression. Okay, so motion of a satellite around a planet in circular path. The same derivation what I am going to do could be used for motion of a planet around the sun. We take it as a circular path there also. Or we can use that motion of a moon around a planet. Everywhere the same derivation. Okay, so here motion of a satellite around a planet. We take the path is circular path around the planet. Mass of the planet is capital M. Mass of the satellite is symbol M. So since it's moving on a circular path, it needs a centripetal force. The required centripetal force is provided by the gravitational force exerted by the planet on the satellite. Required centripetal force is provided by the gravitational pull by the planet on the satellite. So that is given by the Newton's law of gravitation. So the required centripetal force is provided by the gravitational force, which is gmm over r squared. So that is the centripetal force. That's going to be mv squared over r. I can get the expression for the speed of the satellite. So make the v subject. Solve it. R squared r get cancelled. Capital M, symbol M will get cancelled. Where M is the mass of the satellite, symbol M. So a mass of the satellite and M will get cancelled. So V is going to be square root of Gm over R. Better remember this equation. You must be able to derive this also. Not a derivation, just simple thing. But remember that the speed of the satellite around a particular planet is inversely proportional to square root of R. Inversely proportional to square root of R. Better remember that. Be inversely proportional to square root of R. Better know that. And you should be able to derive it. Okay, we need this equation to explain how did they identify dark matter. The same thing, I'll do it, but same idea is used there also to the experimental evidence where they identify the dark matter. Right, okay, in under cosmology. Okay, so same thing I can continue. If I want, I can say V equal R omega and I can get an expression, or I can substitute here r omega squared. Anything I can do. I can substitute here mr omega squared and do it again. Or even I can say V is equal to square root of gm over r, or V squared equal gm over r. I take the square of it, gm over r. But V equal r omega, we know that V equal r omega means r squared omega squared. We know that V equal r omega, we learned that in circular motion. So r squared omega squared equal gm over r. Omega, we know that omega equal 2 pi over t. So substitute here, cross multiply r cube into omega 2 pi over t, all things squared equal gm. So t squared will be the subject, 4 pi squared. So from this, t squared is equal, make the t squared subject, is equal to 4 pi squared over gm times r cube. So for a given planet around it, Satellites can move at different radius, different distance from the center of planet. Everything should be measured from the center. So the period of the circular motion, so m is constant, g is constant, 4 pi squared is constant. So t square proportional to r cube. Important conclusion. T square proportional to r cube. You should be able to derive this. Whenever there is a question related to time period of circular path around circular path of a satellite around a planet, or motion of a moon around a planet, or motion of a planet around the star or sun, the same way we have to derive it. So even if it is a numerical calculation, you have to derive it and get it. Don't memorize this equation and don't use this directly without derivation. You will lose a lot of marks. So you have to derive it. Simple, the derivation. Remember the derivation. This is called Kepler's law. The derivation is called, the outcome, the final conclusion, T square proportional to R cube, is one of the Kepler's law. We call in your syllabus just Kepler's law. Okay, so first question based on what we learned so far. It's an explanation type question. A satellite is orbiting a planet of mass m at a speed v, a constant speed v, at distance r. So it will satisfy this equation, t equal square root of gmor. You can't use it directly, you have to derive and get it. Not a derivation, just one line you can get it. Okay, so the motion of the satellite around the planet of mass m, it has speed v, right. The question is, due to some reason, or maybe collision with something, the speed of the satellite suddenly drops. The speed of the satellite suddenly drops. What will happen to its following motion? Okay, so the speed suddenly drops due to collision with something else. The speed of the satellite suddenly drops. What will happen? There is no change in the direction immediately. Suddenly drops when it is at particular height h, at a particular distance r from the center of the planet. The speed only suddenly drops. What will happen to its motion next? Okay, so for that, students mostly answer like this. They use this equation, v equals square root of gm over r, where m is the mass of the planet, r is the distance of the satellite from the center of the planet. So the speed of the satellite suddenly drops. So v becomes lower. So when v decreases, g and m constant, so r should increase. Friends normally say when v decreases, r should increase. So the satellite will move away, outward spiral path. It will move away, it will spiral out and move away from the planet. That's the answer most of the students they give. Okay, careful, that is not the answer. Actually, you know, v equals square root of gmor. How we obtain, we derive this equation? We said that when the satellite is in circular path, it needs a centripetal force. So the required centripetal force is given by mv squared over r according to circular motion. It needs a centripetal force that is equal to mv squared over r. That's a required centripetal force to move on a circular path. When it has this centripetal force, it's provided by, physically, it's given by the gravitational force between the planet and the satellite. That provides the required centripetal force. So this is the required centripetal force when it is at a particular distance r from the center of the planet. That is provided by the gravitational force. It's a type of force. Gravitational force is a type of force. That force provides the required centripetal force. Now what happens? The speed suddenly drops. When the speed suddenly drops, the required centripetal force is decreasing. The required centripetal force is suddenly dropping. So when the required centripetal force suddenly drops at that position, the gravitational pull given by the Earth on the satellite, or the planet on the satellite, will remain the same, but the required centripetal force is dropping. That means the gravitational pull now becomes larger than the required centripetal force. So the gravitational pull becomes larger than required centripetal force. Means what happened? The satellite will move in an inward spiral path and fall on the planet finally. Because the required centripetal force is dropping, The gravitational pull remains same as earlier. Now the gravitational force has become greater than the required centripetal force. So the satellite will have a force which is more than the required. Imagine something like a small sphere, a marble or a bob is attached to a string and you are rotating on circular path. Suddenly you pull a small pull towards it. You rotate it in a circular path. The string provides the tension, provides the required centripetal force. Suddenly give a small greater force, greater tension. Just pull it. When you pull it just that, the marble will come towards you. So like that, the satellite will start to move in an inward spiral path because it won't just fall because it has velocity or speed along the tangent at that moment. So it will move on an inward spiral path and finally fall on the surface of the planet. That's the answer you should say. Okay, so this type of questions normally come. Right, mass of planet X is m and its radius is 2r. Gravitational field strength on its surface is g. Mass of planet Y is 2m and its radius is 3r. Find its gravitational field strength on its surface means we need to give it in terms of g. Okay, so for X we can write g equal gmo r square. I'm going to use this equation. So g equal g, the mass is m over r square, that is 2r all in squared. So that will be gm over 4r squared. First equation. For y, for the planet Y, I need to find g1. I'm going to use the same thing. G instead of mass, I should put 2m. The mass is 2m. G times 2m over 3r all in squared. So that will be 2gm over 9r squared. Second equation. Now nothing. Divide second equation by first equation. You will get the g1 in terms of g. So second equation divided by first equation. g1 over g equal 2gm over 9r squared into, this will go up, 4r squared over gm. So that will be r squared will get cancelled, gm will get cancelled, 8 over 9. So g1 is going to be 8g over 9. Okay, so that is g1 is going to be 8 over 9g. Okay, so the third question, weight of an object on the surface of a planet is 120 Newton. Find the weight of this object at a height of 60 km from the surface of the planet. Radius of the planet is 7,200 kilometers. So the weight means that's a gravitational pull, gravitational force between the object and the planet. So that could be given as F equal g m over r squared. Okay, r must be measured from the center of the planet. Okay, on the surface of the planet, the weight is given as 120 Newton. So 120 is equal to g m over r squared is on the surface means that must be the radius of the planet, 7,200 into 10 to the power 3 all things squared. Let it be first equation. Now the question is, what will be the weight of the same object at a height of 60 km from that planet? So weight I need to find, let it be W is equal to g m mass of the planet m over, it's from the, at a height of 60 km from the surface of the planet. So at a height of 60 km from the surface of planet means from the center the equation must be used when you use. So that's going to be radius plus 60 km. Radius is 7,200. So 7,200 plus 60, 7,260 into 10 to the power 3 all things squared. Okay, I need to find the W, so it's not a big issue. Divide the second equation by the first equation. So divide the second equation by the first equation. That is W over 120 equal to GMM over 7,260 10 to the power 3 all things squared into, this will go up when I divide it, that is 7200 into 10 to the power 3 all things squared over GMM. Okay, GMM will get cancelled, 10 to the power 3, 10 to the power 3 inside the square will get cancelled. So W is going to be, W is equal to be 7200 over 7260 all things squared into 120. Find the W. So you'll get 118 Newton, 118 Newton. Okay, so the next question, question number 4. Period of the moon around the earth is 28 days. Find the distance or height of the moon from the surface of the earth, which is radius of the earth is 6370 kilometer. Mass is given, I forgot to write it. Mass of the earth is also given. Mass of the earth 6.02 10 to the power 24 kilogram. Okay, so by using this we need to find the height of the moon above the surface of the earth. Okay, so for this type of question we should start from the basic principles, that is the required centripetal force, that is mr omega squared, is provided by the gravitational pull G m2 r square. G mass of the earth, mass of the moon over r square. So m mass of the moon and the mass of the moon will get cancelled. So r squared into r cube. Omega means we know that omega equal 2 pi over t in circular motion. So into 2 pi over t all things squared is equal to Gm. So solve it and make the t subject, t squared equal 4 pi squared over Gm into r cube, or you can make the r cube subject because we are going to take the r, the height we are going to find. So we will make the r cube subject. So r cube is going to be, r cube is equal to Gm over 4 pi squared times t squared. Gm over 4 pi squared t squared. Okay, so now we need to find the radius of the orbit of the moon from the center of the earth. From that we will subtract the radius of the earth. Okay, so we will substitute, that is G 6.67 10 to the power minus 11. Mass of the earth is given 6.02 10 to the power 24. The mass of the moon got cancelled. Symbol M is the mass of the moon, that got cancelled. So over 4 pi squared into t squared. T squared means the square of the period, that's 28 days. We have to give it in seconds. So 28 days, we need to convert to hours. So 24 hours per day. Then 60 minutes into 60 seconds all thing squared. Okay, solve it and find the r. So you will get r cube, the value you will get it when you solve the right side, that will be the value of the r cube. Take cube root of it, you will get the r, the value of r will be equal to 3.90 10 to the power 8 meters. In kilometers it will be 3.90 10 to the power 5 kilometers. So that's the radius of the orbit of the moon from the center of the earth. The height of the moon is the question. So height of the moon from the surface of earth is radius of the orbit minus radius of the earth, is it? So this is the earth, this is the orbit. So we know the radius of the orbit. Radius of the orbit, from that we subtract the radius of the earth, we will get the height. Okay, so the height we need to find it. That's radius of the orbit 3.90 10 to the power 5 minus radius of the earth is given, which is 6,370, that also in kilometers. So solve it, subtract it, you will get finally 3.84 10 to the power 5 kilometer. That's the height of the moon or distance of the moon from the surface of earth. Check it with internet, type it in the Google height of the moon above the surface of Earth, you will get exactly the same answer. Okay, so the fifth question, mass of the Earth is 6.0 into 10 to the power 24 kilogram and its radius 6,370 kilometers. Normally, sometimes in the past paper they say 6,400 kilometers. This is 6,370 kilometers. I think this is more accurate value. Find the height of the geostationary satellite above the surface of Earth. Geostationary satellite. Geostationary satellite means the satellite that has period equal to 24 hours, it always moves up, its orbit is above the equator of the Earth. So for the certain region of the Earth, it looks like stationary related to Earth. So the period of the Earth is 24 hours, same as this period of spin of the Earth, that also 24 hours. So this satellite also has the same period, 24 hours. Probably the satellite, the geostationary satellite is parked above the equator of the Earth. Okay, so they asked to find the first part, the height of the geostationary satellite, which has period 24 hours. So geostationary satellite, if they say the period is 24 hours. So same equation what I used earlier. First part, F equal, that is mr omega square, that's a required centripetal force which is provided by the gravitational force gmm over r squared. Capital M is the mass of the Earth, symbol M is the mass of the geostationary satellite. Mass of the geostationary satellite will get cancelled, r squared here, r cube into omega equal 2 pi over t. So that is 2 pi over t all things squared is equal to gm. So find the r cube, make the r cube subject. R cube is going to be gm over 4 pi square into t squared. So substitute the values and find the r. 6.67 10 to the power minus 11. Mass of the Earth is 6 into 10 to the power 24 over 4 pi squared into t squared, 24 hours. So 24 into hours to minute, minute to second, all things squared. That is r cube. Find the r, solve it on the right side and take cube root of it. So you will get r is equal to, you will get r that is equal to 42.30 10 to the power 6 meters. In kilometer, if you find, that is going to be 42,297 kilometers. So this is approximate value, 42,297 kilometers. So the height of the satellite is equal to radius of orbit minus radius of the Earth, as I explained, same as earlier for the moon. So r we know 42,297 minus radius of the Earth is 6,370 kilometers. So that is going to be 35,000. The height is 35,927 kilometers. That's the height of the geostationary satellite. Check it in the Google, height of the geostationary satellite. It says 35,786. Slightly different because mass of the satellite is, mass of the Earth is not 6 into 10 to the power 24. I think something 5.97 or something. Anyway, we use 6 into 10 to the power 24. Anyway, the internet, the standard value, it says 35,786, around 120 kilometer different. Doesn't matter, we are getting a good answer for this calculation. Okay, second part, find the speed of it. So that we can simply find v equal r omega. Or we can use this equation, derive and get it. Derive and get it. You can't directly use this equation. This is not a standard equation. You have to derive it and get it. Okay, so v equal r omega. Omega equal 2 pi over t. We can use that equation. So r, we found it here. 42.30 10 to the power 6 omega 2 pi over t. T is 24 hours, so 24 into 60 into 60. So this much of meter per second. Solve it. We will get the speed which is 3076 meter per second. Or if you are using this one, you must derive it from basic, the initial, you have to derive it and get it. So again I'll show the derivation. It's like this. We have to derive it means like, let's start with or the gravitational force, the required centripetal force is mv squared over r, which is given by gravitational pull gmm over r squared. So mass of the satellite get cancelled. So v squared is equal to gm over r. So v is equal to square root of gm over r. Okay, so substitute the values. Square root of g, that is 6.67 10 to the power minus 11. Mass of the earth given 6 into 10 to the power 24 over r, we found it in the previous part, that is radius 42.3, 10 to the power 6 meters. Solve it, you will get exactly same answer. Maybe it's 3075, you will get 3075 meter per second. Either way you can do. Okay. Okay, so sixth question. By deriving an appropriate equation, show that the orbital speed of a satellite decreases as the radius of the orbit increases. So that is actually they asked me to derive this one. Anyway, I don't need to derive again, I already derived it. So first part, just we leave it. Okay, second part, by deriving an appropriate equation, show that the orbital period of a satellite increases as the orbital speed decreases. Okay, so for that we can show like this. Okay, so from this one, first derivation, second part I am deriving it. From the first derivation that we can derive, already derived it. So v is equal to square root of gm over r. So from that v squared equal gm over r. Okay, so by deriving an appropriate equation, show that the orbital period increases as the orbital speed decreases. So I need to get a relationship between period and the speed. Okay, so there we can say speed v is equal to 2 pi r over t. 2 pi r is the circumference over t is the time taken for one complete orbit. So here we can say from this I'll substitute r by v, this equation. So from this I would eliminate the r because second one is some relation between speed and the time period. So from this I'll substitute r in terms of v. So r is going to be gm over v square. Substitute that here. So v is going to be 2 pi over t into, instead of r, gm over v squared. Okay, nothing. So they are saying period of this. So make the t subject. So t is going to be, make the t subject 2 pi gm over v cube. So that is t proportional to, inversely proportional to v cube. So when the speed increases, the orbital time period will decrease. Okay, so the seventh question, first part, there are three parts. First part is a past paper question. Radius of the earth is 6,400 km and the gravitational field strength on its surface is 9.81 Newton per kilogram or meter per second squared. Okay, whatever it is same. Find the gravitational field strength at a height of 40 km from the surface of Earth. So we are going to use G equal Gm over R squared. So G equal Gm over R squared. So on the surface of Earth, 9.81 equal Gm over R squared, 6,400. I don't need to convert to meter because I'm going to divide two equations. The 10 to the power 3 will get cancelled. But anyway, to avoid unwanted confusion, I included 10 to the power 3. Okay, so Gm over R squared. The question is find the gravitational field strength at 40 km from the surface of Earth. At a height means from the surface of Earth. So you know the equation is applicable are always from the center of the Earth. So G1 I need to find. So G1 is equal to Gm over 6440 into 10 to the power 3 all things squared. So that's a second equation. Divide second equation by the first equation. G1 over 9.81 is equal to Gm over 6440 into 10 to the power 3 all things squared into 6400 into 10 to the power 3 all things squared over Gm. Gm get cancelled, 10 to the power 3, 10 to the power 3 get cancelled. So 6400 over 6440 all things squared. So G1 is going to be 6400 over 6440 all things squared into 9.81. So that will be 9.69 meter per second square or Newton per kilogram. Okay, so the Earth is represented by a circle in the diagram below. Add to the diagram to indicate the gravitational field strength. So you know, how do we identify the gravitational field strength? The direction of the force or the gravitational force acting on a test mass indicates the direction of the gravitational field. So if I keep a test mass, a tiny mass, it will be pulled by the Earth, so the force will be towards it. So always the gravitational field lines are towards the center of the planet. Draw a few lines, symmetrical. Here also the gravitational field lines indicates the strength of the field. Number of lines per unit area indicates the strength. The gravitational field lines never cross each other. Don't draw gravitational field inside. Normally you don't draw inside the planet, outside the planet, but they should point towards the center of mass. So if I extend these gravitational field lines, they will meet at the center of mass of the planet. So gravitational field lines never cross each other. The number of lines per unit area indicates the strength of the field, same as the electric field, but here it's like a radial field. Arrows are towards the center of the planet. Okay, so explain why the gravitational field can be thought of as approximately uniform over a smaller region of the Earth. Even if the Earth is spherical shape, if you think about a region, for example, a football ground, it looks perfectly flat. So the gravitational field lines are always radial, means they will be perpendicular to the surface at any point because they meet at the center of the Earth or center of the planet. So if you consider smaller region of the Earth, at every point, the gravitational field lines are perpendicular to the surface, and if you draw the smaller portion, looks like a flat line, all the gravitational field lines are perpendicular, means the gravitational field lines appear parallel among them. Therefore, the strength of the field is the same in a smaller region when you consider above the surface of Earth. Okay, so the 8th question, this is also a past paper question. In binary system of black holes, two black holes are at a separation of 3.2 10 to the power 15 meter and their masses are given. The black holes orbit about a point 7.7 10 to the power 13 meter from the larger mass black hole. That means they will orbit about the common center of mass of the black hole, common center of mass. That means imagine if there's a larger sphere, a steel sphere, massive mass, not larger, not in size, a massive mass, M1. There is another sphere, the same size, we can imagine, M2. M2 is lighter. Both are connected by a light rod like this, Okay, so when they are connected by a light rod, the center of mass of this system will be closer to the massive sphere. That's the center of mass. Now about the center of mass, you rotate it. So this will rotate about this one. So the radius of the orbit of this one will be this one. This will rotate about this way. This will rotate with the radius of, this is the radius of orbit for the M1. This is R1. This P is the center of mass of the system of two spheres. The rod which connects them much lighter, so we can neglect its mass. So if you use the center of mass equation, sigma mi xi over sigma mi, so you don't need it, but I'm just telling. So they are orbiting about point P, means this mass will orbit in a circular path of radius R1. This will orbit at a radius of R2. From P to this one is the R2. So from P to the mass M2 is R2. That will orbit in a circular path of radius this one. So like this. So that is, imagine on this plate, on two sides, spheres are attached, massive sphere, lighter sphere. By holding it at the center of mass, rotate it. So when you rotate like this, both will have the same period of circular motion, is it? When this is here, this is here. When this comes to this point, this will be here, like that. They will have the same period of circular motion, but they will orbit about the common center of mass. Same way, here the two black holes, they are forming binary system. Binary system means a combination of two massive objects like stars or black holes. They together form a binary system. They are orbiting about point P. Point P is the center of mass. Calculate and see, you'll get 7.8 10 to the power 13. I don't know why they give 7.7. Anyway, it's okay. We will use the given data. So they are orbiting about point P, right? Show that the orbital period of the binary system is, both will have the same period. This will orbit about point P. This also will orbit about point P. Both will have the same period of circular motion. So if I know that, I need to find the time period. How can I find the time period? The idea, so here first we will find the gravitational force, because when the massive mass orbit about P, it needs a centripetal force. So wherever it stays, this will be in opposite to its position. So the force from acting on the massive mass towards P is the gravitational force or gravitational pull exerted by lighter mass on the massive mass. Same way, when lighter mass or lighter or low mass black hole also orbiting about P, means the low mass black hole also needs a centripetal force. The centripetal force is the gravitational pull exerted by massive black hole on the lighter black hole. So we need to find the gravitational pull or gravitational force between the two black holes. That is going to be the centripetal force, because the gravitational pull on this one will act towards the lighter black hole, means that will act towards the center of mass P. Same way, the gravitational force on lighter black hole also will act towards point P, because it will act towards the massive black hole. So we will find the gravitational force between the two black holes. F equal G m1 m2 over r squared. 6.67 10 to the power minus 11. Mass m1 is 1.6 into 10 to the power 39. Mass m2 is 4 into 10 to the power 37 over r squared is the distance between the two black holes, that is 3.2 10 to the power 15 all things squared. So find the gravitational force. That will be equal to 4.17 10 to the power 35 Newton. So that will be there. This force is a centripetal force for the circular motion of massive black hole about P, and this is the same force is the centripetal force for the lighter black hole for its circular motion about P. So I can use now F equal mr omega square. F I know, R I know. For the massive black hole, R I know, because it's given 7.7 10 to the power 13. F equal mr omega square. We will find the omega. Omega equal 2 pi over t. We will find the t. So if I find the time period of this one, that is same as for this one also. If you want, you can use F equal mr omega square for this one. Then you had to use the distance of this one from the P. So that you had to subtract 3.2 10 to the power 15 minus 7.7 10 to the power 13, you will get this one. But anyway, that also you can do, but since I know this distance, I will use for the massive black hole. So F equal m r omega squared for massive black hole. F we know 4.17 10 to the power 35. Its mass is 1.6 10 to the power 39. Is it? R, the radius of orbit 7.7 10 to the power 13. In omega square, omega equal 2 pi over t all things squared. So 2 pi over t all things squared, I can say 4 pi squared over t squared. Solve it and get the find the t. So you'll get t is equal to 3.415 into 10 to the power 9 seconds, you will get it. But they asked to show that 100 years. So I need to convert this into years. Okay, I'll erase this part now. Okay, so t is equal to 3.415 10 to the power 9 seconds. I had to convert to years means seconds to minutes, divide by 60, minutes to hour, then hour to day 24, into day to years 365 years. Solve it, you will get 108 years. So approximately 100 years. Okay, so the ninth question, it is claimed that a satellite in orbit at a height of 8.50 10 to the power 5 meter would make 15 orbits of the Earth every 24 hours. This 15 look like IS, it's 15 orbits of the Earth every 24 hours. Assess the validity of this claim. Mass of the Earth is 5.98 10 to the power 24 kilogram. Okay, so here I am going to use the equation what we used so far, t squared equal 4 pi squared gm over gm into r cube. Anyway, if you must derive that equation, or they might ask you to derive it in the previous part. Anyway, I'll use F equal, the required centripetal force equal mr omega squared equal gmm over r squared. M will get cancelled, so r cube into omega means 2 pi over t all things squared equal gm. So make the t squared subject. T squared is equal to 4 pi squared over gm into r cube. Okay, so at a height of 8.50 meter above the surface of Earth, so it's orbiting around the Earth. So the mass of the Earth is given, the radius of the Earth is also given. Sorry, I forgot to write it. Radius of Earth is 6,360 kilometers. That's the way it's given. 6,360 kilometers. Okay, that's the radius of the Earth. So radius of the Earth also given. So this is the height. So we know if this is the Earth, the radius of the Earth we know that is 6,360 kilometers. But the satellite is orbiting at a height of 8.50 10 to the power 5 meters. So when we use this equation, r must be the radius of the orbit. R must be radius of the orbit means height plus radius of the Earth. That's a very common mistake students make. They don't add the Earth of radius of the Earth when the height is given. So you have to add the radius of the Earth with the height of the satellite above the surface of Earth. Then only you will get the radius of the orbit of the satellite. Okay, so we'll continue. we'll find the time period here. So from this, t squared is equal to 4 pi squared over g, 6.67 10 to the power minus 11. Mass is given, mass of the planet, that is mass of the earth, 5.98, 10 to the power 24 into r cube. So radius means we have to add both, that is 8.5, 10 to the power 5, that is in meters, this is in kilometer, convert to meter, 6360 into 10 to the power 3 meters all in cube. Okay, so after that, find the t squared and take square root of it. You will get t is equal to, solve it, you will get t is equal to 6091 or 90 second, 6091 second you will get it. Okay, so the period of the earth is 24 hours, is it? They are given it every 24 hours. So during 24 hours, how many times will it make complete orbits? We know the time period of the orbit. So how many times will it orbit during 24 hours? Divide the 24 hours, first convert the 24 hours into second, divide it by the time for one orbit. You will get the number of orbits during 24 hours. Equal 24 hours 60 minutes into 60 seconds divided by 6091. So you will get almost 14.2 orbit, approximately 15 orbits. It should be 14, but most closest value we take it 15. Yeah, it's okay. Okay, so this is May 2022, June 2022, question number 16. Part A, nothing, we several times came across, we have to show t squared proportional to r cube, that's a Kepler's law. So I am not doing it. A part, first part, just nothing. A part, second part, it says when planets align as they orbit the sun, they are said to be in opposition. The diagram shows the Earth and Jupiter in opposition. So that means this is Sun, this is Earth, this is Jupiter. This diagram is given in the question. This is Sun. So the opposition means they are on the same line. Sun, Earth, Jupiter, they are on the same line. Then it's called opposition. The website states that the Earth and Jupiter are in opposition every 13 months. Okay. So deduce whether this statement is correct. Mean distance from Earth to Sun. So this distance, Earth to Sun, this radius of orbit of the Earth is given. That is radius of orbit of the Earth is given as 1.5, 10 to the power 11 meter. Radius of orbit of the Jupiter is given, that is 7.8, 10 to the power 11 meter. Okay, so Earth orbit, the time period is also given. We know that 12 months, 1 year, so it's given 12 months. So we need to show that the statement is correct. Every 13 months, the Sun, Earth, Jupiter becomes in opposition, means they come on the same line. Okay, so the idea is this one. They are in same line like this now. Later, according to the equation, t squared proportional to r cube means the planet that has smaller radius of orbit, that means which is closer to Sun, will have shorter time period. Which is closer to Sun or smaller radius of orbit will have smaller time period. And also we know that they are going to orbit in different time periods. They will have different time periods. We know that omega equal 2 pi over t, and also we know that omega equal theta over t. Omega equal theta over t, because theta is the angle of as central angle, change in central angle over time taken t. Okay, so we know that the planet that has larger time period, that means which is far away from the sun or which has larger radius of orbit, will have larger time period. Larger time period means when we consider particular time, during the time the angle in the change in central angle will be smaller. Change in central angle will be smaller. So when we consider what will be their position from this time, they are in opposition. Okay, later at time t, from this position, we take this position as at time t equals 0. Later at time t, what will be their position means the Earth, which has smaller radius orbit, that has smaller time period. Smaller time period means angular speed is larger. Angular speed is larger means change in central angle will be large. Angular speed larger means same change in central angle will be larger for Earth at a time t later. So Earth might be from this position, Earth might be somewhere here at time t, which it would have gone through angle theta 1. But Jupiter that has larger radius of orbit means larger time period. Larger time period means at a particular time the change in central angle will be smaller for Jupiter. The Jupiter might be somewhere here. That might make an angle theta 2 which is smaller with the center of the orbit. So that is going to be theta 2. Okay, so the condition mathematically when they are in opposition again, theta 1 minus theta 2, that's change in central angle, theta 1 minus theta 2 should be 0. That happened now. Theta 1 minus theta 2, the difference between the central angle 0 means that happened now when t equals 0. Later, when they become again opposition, theta 1 minus theta 2 could be 2 pi. We don't know they will come and meet at the same position, we can't say. Maybe this would have completed 5 orbits, this would have completed 4 orbits, means theta, the change in central angle of the Earth minus change in central angle of the Jupiter, when it is 2 pi, there it will happen again, they will be in opposition somewhere here, we don't know at this position. Again, when the change in central angle becomes 4 pi also, they will be again in opposition. So like that, when the change in central angle, that is when theta 1 minus theta 2 is equal to 0, that happened now, or 2 pi or 4 pi or 6 pi, 8 pi, like that 2 and pi, general format 2 and pi, they will be in opposition where n is an integer, n equals 0, 1, 2 and so on. So it's an integer. So during that time, then when theta 1 minus theta equals 0, 2 pi, 4 pi, 2 and pi, then they will be, or these planets will be in opposition. Okay, so we need to find theta 1 minus theta 2. From this we can get theta is equal to generally 2 pi over t, that's a period, into t. So I'm going to use this one here. So omega equal 2 pi over t, that is change in central angle during time t. So that time t, when will it happen? We have to show during that time t, if theta 1 minus theta 2 for the two planets, the difference between the change in central angle becomes 0 or 2 pi or 4 pi, that is 2 times 2 pi times into n is an integer, then the planets will be in opposition, they will be in the along the same line. Okay, so I need to find the time period for the Jupiter, because time period for the Earth is given. I need to find the time period for the Jupiter. Okay, that's nothing. I'm going to use the first part, A part, first part. They asked to derive t square proportional to r cube. I'm going to use that t square proportional to r cube. We derived in the A part, first part. So from that, t square is equal to a constant times r cube. The constant is 4 pi squared over gm. Anyway, I'm not going to substitute anything. So for Earth, we know t squared is 12 months. 12 squared equal k into the Earth radius is 1.5, 10 to the power 11 all in cube. Let it be first equation. For the Jupiter, I need to find the time period. Let it be Tj. That is going to be k into Its orbit is 7.8 10 to the power 11 all the cube. Second equation. Divide the second equation by the first equation. I'll continue here. Second equation. Divide the second equation by the first equation. You will get Tj. Sorry, this T squared, is it? T squared J. So T squared J over 12 squared is equal to 7.8 10 to the power 11. 10 to the power 11 over 1.5 10 to the power 11 all the cube. I can take the cube out, then solve it and find the square root of it and find the time period of the Jupiter. You will get 142.3 months. Okay, so I know the condition. If they want to be in opposition again, the condition theta 1 minus theta 2 should be either 0, 2 pi, 4 pi and 2n pi. Generally, I can say n is equal to 0, 1, 2 integer, right? So, theta 1 minus theta 2, theta equal to 2 pi over t, the period into t. So, theta 1 minus theta 2 means 2 pi over t Jupiter. Yeah, the largest angle for Earth, so t Earth minus 2 pi over t Jupiter into t, because here t comes 2 pi over t into t minus 2 pi over t into t. The t I took it common is equal to 2n pi, because they ask every 3 months. So they are asking every 13 months. So they didn't say after 13 months, every 13 months. So that's the reason I did it in generally with n. Most students ask, why are you doing it including n? Why can't you put just 2 pi? Okay, if the question is, website states that the Earth and Jupiter are in opposition during next 13 months, then I don't need to put n equal, I don't need to include n here, just I can put 2 pi. But every 13 months means, yes, 13 months, then again 26 months, again 39 months and so on. So that's the reason I put n here, general format. Okay, 2n pi. Okay, we'll substitute and find the t. So 2 pi, 2n pi means I can take I now 2 pi into n, the 2 pi here, this 2 pi will get cancelled. So 1 over Te, time period of Earth is, I'll give it in months, that is 12. 1 over 12 minus 1 over 142.3 into t is equal to 2 pi got cancelled, n. What is n? N equals 0, 1, 2, 3 integer. Okay. So solve it. Find the t. Now 1 over, you can use the calculator, 1 over 12 minus 1 over 142.3 into t equal n. So find the t. You will get at t is equal to 13.1 n, where n equal 0 already over because that happened now. Next 0 over 1, 2, 3 and so on. So that means if I substitute 0, t equals 0, that happened now. Then if I substitute n equal 1, n equal 1 means after 13 months. N equal 2 after 26 months. N equal 3 after 39 months. So general format 13.1 n, where n equals 0, 1, 2, 3. Therefore, they will be in opposition when t equal 13 months or 26 months, or I can put on 13 months and I can put, because many solutions, 13 months. Okay, 26 months I put just comma, 39 months, because every 13 months, yes. So the difference between this is 13, 26 minus 13, 13, 39 minus 26, 13 and so on. That's the answer for this question. Okay, so the next topic is gravitational potential, something like electric potential what we learned in unit 4. Here gravitational potential. When there is mass m, for example, when there is planet or moon, it will create gravitational field around it everywhere. The same way it will create gravitational potential around it everywhere. So what is the gravitational potential of a mass m means? Mostly in your syllabus we take a spherical shape object, spherical shape mass, planet or moon or star. So if there is a planet or star or moon of mass capital M at distance r from its center of mass at point P, what is the gravitational potential of this mass capital M at point P means? How do we define? Okay, definition, careful. Work done in moving 1 kilogram mass from infinity to point P is defined as the gravitational potential at point P. Again, I say work done in moving 1 kilogram mass from infinity or infinite distance to point P is defined as the gravitational potential at point P. You know, gravitational force is always attractive. So gravitational force is attractive means actually when a 1 kilogram mass is moved from infinite distance to point P, the gravitational pull exerted by the mass capital M or planet will do work on the object of mass symbol M, 1 kilogram, mass capital 1 kilogram, and this mass will gain kinetic energy. So when it gains kinetic energy, it will lose its gravitational potential energy. Since the force is attractive, the gravitational potential will be always a negative quantity because its gravitational potential will decrease when the object moves from infinity towards the object of mass m. When 1 kilogram mass moves, the gravitational potential of this created by this mass m will decrease when the distance of it from the mass decreases. So the gravitational potential is always negative because of the attractive force between the mass m and the 1 kilogram mass. So we can say why the gravitational potential is negative means because of attractive force, the gravitational potential decreases when the distance from the mass decreases. Okay, so the gravitational potential at point P is given by V equal minus Gm over R. You must know that the gravitational potential is given by minus Gm over R. Okay, so when a mass m is kept at point P, when a mass m is kept at point D, the gravitational potential energy of the mass m, I told that in unit 1, in unit 1 work energy power, we never measure the gravitational potential energy in unit 1. We measure the change in gravitational potential energy. If the mass moves up, we write mgh, which is the gain in Gp. When the mass moves down, we write loss in Gp. So we never measure the gravitational potential energy in unit 1 when we do questions related to gravitational potential energy. But here we can measure the we can calculate the gravitational potential energy of mass m when it is kept in the gravitational field created by mass capital M. So the gravitational potential energy of object, it could be a small object, a satellite or whatever it is, the gravitational potential energy of this object of mass symbol m when it is in the gravitational field of gravitational field created by the mass capital M at distance r from it, the gravitational potential energy is given by gravitational potential into the mass of the object. So the gravitational potential is minus Gm over r into m. So the gravitational potential energy of the mass is always negative. The reason here also, when the distance of the mass m from the massive mass m decreases, its gravitational potential energy will decrease. So that's the reason it's given by a negative quantity. So the gravitational potential energy is given by minus Gm over r into m, that is V gravitational potential into mass. Okay, so the unit of gravitational potential is joule per kilogram, because we define work done in moving 1 kilogram charge. So that means work done per kilogram, joule per kilogram is the unit of gravitational potential. The unit of gravitational potential energy is joules. Okay, so the next topic is change in gravitational potential energy. Okay, so for example, there is a planet. The radius of the planet is r. The center is O. The center of the planet is O. So an object is moved, object of mass m is moved from point P1 to point P2. So we know that when the distance from the planet decreases, the numerical value will be with larger number with negative sign. That means when object moves closer and closer to the planet or moon or whatever it is, the gravitational potential energy will decrease. I told already, kinetic energy will increase of the moving object. So for example, gravitational potential energy decrease means it will have a negative larger value. Say for example, minus 10 joules is less than minus 4 joule when we consider the gravitational potential energy. This is a smaller value, negative sign. Okay, so when object moves away from the planet, what will happen? It will gain gravitational potential energy. So imagine a point P is at a distance r from the center of the planet. So this distance is r from the center of the planet. The R1 will make it as R1. So it's moving from P1 to P2 through a height h or distance h from it. So what will happen to the gravitational potential energy? So it will move away from it. So it's going to, the object of mass m is going to move from P1 to P2. So gain in gravitational potential energy, gravitational potential energy of the mass m when it moves from P1 to P2. So gain means final minus initial. So the gravitational potential energy at point P2 is V2m minus V1m. V2 is the gravitational potential of the planet which has mass capital M at a distance of P2, that is R1 plus h is the distance of P2 from the center of the planet. So the gravitational potential energy of the mass m at point P2 is V2 into m, that is gravitational potential of the planet at point P2 into mass. That's I told that, yeah. And the gravitational potential energy of the same mass at point P1 is V1m. Okay, so we'll continue this. So V2 is equal to minus Gm over distance of point P2 is R1 plus h minus, again there will be minus, so minus Gm over R1 into m. Okay, so solve it, minus into minus plus, so it's going to be Gmm over R1 minus Gmm over R1 plus h. H is the distance or height through which the object of mass m is moved from P1 to P2 such that away from the planet. Okay, we'll find the gain in gravitational potential energy. So I'll put equal sign because I can say delta gravitational potential energy, delta potential energy, we'll see delta PE, delta PE. So that's going to be, solve it this one, Gmm, you can take common within the bracket, 1 over R1 minus 1 over R1 plus h. So solve it, Gmm, R1 plus h is the LCM, R1 plus h minus R1. Okay, so it's going to be Gmm R1 over R1 into R1 plus h. Okay, now this is the increase in gravitational potential energy. Okay, now we'll see, we'll analyze it. If R1 is very small, if h, the height through which it moved, the height through which the object is moved, h is much smaller than R1. Say the point P1 is at a distance R1 from the center of the Earth. The distance through which the object of mass m is moved is h. If h is very small compared to R1. So for example, this may be around 7,000 kilometers. The distance moved may be around 200 meters, something like that. So if h is very small, if h is much smaller than R1, then what can we say? Then R1 plus h is equal to, approximately equal to R1, is it? R1 plus h will be equal to, almost equal to R1. So then what will happen? The change in gravitational potential energy, delta potential energy, will become Gmm into R1 over, sorry, here there's a mistake I made. Yeah, this is h. Sorry, there's a mistake. This is h. Yeah, R1 get cancelled, h over. So this is h over. H becomes R1 plus h is almost equal to R1, means it's going to be R1 squared. So this I can write Gm over R1 squared into h times this m will be there. So Gm over R1 squared into mh. Gm over R1 squared. What is Gm over R1 squared? Gm over R1 squared is the gravitational field strength at point P1. So that I can say G1. So G1, that is the gravitational field strength of the planet at point P1 is G1. So G1 mh. So that is going to be m1. Sorry, that's going to be mg1h. So that is the change in gravitational potential energy, mg1h, where g1 is the gravitational field strength at point P1. So this is format we used in unit 1, mgh, the gain or loss, because the distance moved, if it is very small compared to the distance of the point from where to where it's moving. So if this height through which it's moving is very small compared to the initial height from the center of mass, if it is very small, then we can say the change in gravitational potential energy is equal to mgh. Okay, so what we learned in unit 1, the same format. An object is projected from the surface of a planet, say from the surface of Earth, at a velocity initially away from the surface at speed u. It moved through a height h, and the speed becomes a drop to v. So there, when it moves away, it's going to gain gravitational potential energy and lose kinetic energy. So gain in gravitational potential energy, we learned that in unit 1, mgh, but that is true only when the height through which it's moved, h, is very small compared to the initial height of the, or initial distance of the object from the center of the mass of the planet. Otherwise you can't use mgh format. Anyway, again I'll derive it. So gain in GPE here, final GPE, that is at this point, we can say potential at that point, final point, Vf into m minus Vi initially on the surface into m. So the final gravitational potential is equal to minus Gm over, the radius of the planet is r plus h into m, minus Gm over r on the surface of the planet into m. So it's going to be minus into minus plus Gm over r is the radius of the planet, minus Gm over r plus h. Same thing what I did, I am doing it again from the surface. Earlier I took two different points outside. Now from the surface, what we are using in unit 1, I am going to show that. So here the change in gravitational potential energy is going to be, so take the LCM r into r plus h. So that will be r plus h minus r into, we can take gmm common. Okay, so here it will become r will get cancelled, h over r into r plus h into gmm. Okay, here also, if the height through which the object moved, that is h, is very small compared to the radius of the planet, that's the way in unit 1 we do. A ball is thrown vertically upwards, so the distance it moved maybe maximum 10 kilometer, even that you can't throw. But a bullet is fired, this height it went is around 500 meters or 1000 meters, 4000 meters. Anyway, even if it is 5000 meters compared to radius of the earth 6400 kilometers, it's negligible, much smaller, is it? So when I can say when h is very much smaller compared to the radius of the planet, then r plus h approximately equal to r. So if I use that equation here again, so the delta potential energy, change in gravitational potential energy, so gmm h over r plus h is almost r, so it's going to be r squared. So that's going to be g m over r squared times m, this m again into h. Gm over r squared is g mh, that we write as mgh. So that's the way we wrote in unit 1, because the height it moves is very small, negligible. But actually, if the height is not small, through which it's moving is not small, this is the final equation. You have to substitute the given numerical values when the height is not smaller compared to the radius of the planet, or not compared to the not smaller than the initial distance from the center of the planet. So here what's happened, it's moved, thrown away, so loss in GP, you can use either this one. If the h is not much smaller, if this is not true, if this is not true, h much smaller than r is not true, then you have to use this as the gain in gravitational potential energy, that is equal to loss in kinetic energy. Loss in kinetic energy means initial kinetic energy half mv squared minus half mv squared. But if this is true, the height through which it moved is very small compared to radius of the planet, then the loss in, the gain in gravitational potential energy will be equal to mgh. So that is equal to loss in kinetic energy half mu square minus half mv square. That's the way we did in unit 1. Okay, so a satellite of mass symbol m is moving on a circular path around a planet which has radius capital R and mass capital M. So the satellite is at a distance r from it. So the total energy of the satellite is the kinetic energy of the satellite plus the gravitational potential energy. Those are the two energies it possesses. So in unit 1 we don't say gravitational potential, that is change in GP. In unit 1 a ball is thrown upwards, it loses kinetic energy, gains GP when a ball or stone moves down, it loss in GP equal gain in K. So here we are not considering change in GP. So here we are calculating the GP, gravitational potential energy of the object. Okay, not change in GP. There we consider change in GP. Okay, so because here everything are measured from the center of the planet, center of mass of the planet, so we are calculating the GP itself, not the change in GP in this topic. Okay, so kinetic energy of the satellite is half m, the mass of the satellite m, the speed is v, half mv squared. The gravitational potential energy is going to be minus gmm over the radius of the orbit is r. So this is the gravitational potential energy. Okay, we learned that when object moves on a circular path around under the influence of gravitational force, the speed should satisfy when it is moving in circular path, v equal to square root of gm over r. I derived it several times earlier in this lesson. So instead of v square, we'll substitute this one. It's going to be half m. Instead of v square, it's going to be gm over r minus Gmm over R. So that means it's going to be Gmm over 2R minus Gmm over R. So 2R is the LCM, so 2R is going to be Gmm minus 2Gmm. So that will be minus Gmm over 2R. That is the total energy of the satellite. Okay, so students normally ask, the total energy becomes negative quantity. What's the meaning of it? Why is it negative? Okay, how to explain it? We'll explain what's the meaning of if the total energy of the satellite equal to 0 or total energy of the satellite equal to positive quantity, what the meaning of it. Then we can come to the conclusion, why does it have a negative total energy? Okay, we know that when the R becomes infinity, that is when it is at far distance, the gravitational potential energy will be equal to 0. When R becomes 0, the gravitational potential energy equals 0. And we know that when object moves away from a planet, it's gaining gravitational potential energy. And when it reaches infinite distance, the amount of gravitational potential energy possessed by the object will become 0. So at infinite distance, the maximum gravitational potential energy it could have due to the gravitational field of the planet is equal to 0. So when it is in the influence of the gravitational field of the planet, not infinite distance, somewhere closer to the planet, it will have a value, gravitational potential energy, lower than 0. So it has a negative GP. Okay, that's not an issue. That is about the meaning why the GP is negative. Right, but why the total energy is negative? What's the meaning of it? So there we can say, first we'll say what's the meaning of total energy equal to 0. If the total energy equal to 0 means the object has reached infinite distance and R becomes infinity, the total energy will become 0. That means when the object reaches the infinite distance or the satellite reaches the infinite distance, the gravitational potential will become 0, and if the object is at rest, just reaches means when the satellite just reaches the infinite distance, if the speed also becomes 0, gravitational potential energy will become 0 when R becomes infinity, and the speed becomes 0 means the total energy will be equal to 0. That means the satellite is at infinite distance without the influence of the planet, without the influence of the gravitational effect of the planet. It has reached infinite distance. The potential energy becomes 0. It could be at rest, so the total energy is equal to 0. That's the meaning of total energy equal to 0. Right. Total energy equal to positive quantity. What's the meaning of it? Total energy equal to positive quantity means it has reached infinite distance. The satellite has reached infinite distance. So R becomes infinity. The gravitational potential energy equals 0. But it has kinetic energy. So it means the satellite is not going to orbit, or it might move in a random path with a particular speed. So it possesses kinetic energy. So it possesses kinetic energy, no gravitational potential energy due to the gravitational effect of the planet. So it will have total energy, a positive quantity. So you know the meaning of both. If the total energy is positive means the satellite has reached infinite distance without the influence of the gravitational effect of the planet, and it has a speed, so it has a total energy which is positive quantity. If the total energy equal to 0 means it has reached infinite distance, so no influence of the satellite planet, so the gravitational potential energy has become 0. Also the satellite might be at rest at infinite distance, so kinetic energy is 0. So in these two situations, the total energy becomes 0 and total energy become in positive quantities. The satellite is not under the influence or effect of the gravitational field. So now we'll compare. If the satellite is under the influence of the gravitational field, it can't have a 0 value, it can't have a positive value, the total energy. Then what could be the possible? It must have a negative value. That's the only way we can explain. I hope you understood. Again, I am explaining, when it is at infinite distance, gravitational potential energy is 0. It could be at rest. So infinite distance means the satellite is not under the influence of the gravitational effect of the planet. So it has come out of the gravitational effect. So its gravitational potential energy is 0 when r equal infinity. It might be at rest. So no kinetic energy. So total energy equals 0. Same way, if the total energy equal positive quantity means it is at infinite distance, gravitational potential energy has become 0, but the satellite might be moving at random path at a particular speed, so it has kinetic energy, so total energy become positive. In these two situations, the satellite is out of the gravitational influence of the planet. So if it wants to be under the influence of the under the influence of the gravitational effect of the planet, the satellite can't have 0 value. Satellite cannot have positive value. So what could be the value? It should have a negative value. So negative value means the satellite is moving under the influence of the gravitational effect of the planet. That's the meaning of it. Okay, so the first question, under gravitational potential, radius of the earth is 6.4 10 to the power 6 meter and its mass 16 10 to the power 24 kilogram. A geostationary satellite of mass 650 kilogram is launched from the equator and reach its orbit of radius 4.2 10 to the power 7 meter. Calculate the increase in gravitational potential energy of the satellite during its launch from the Earth's surface. Okay, so increase in gravitational potential energy. So there the increase in gravitational potential energy delta GPE is equal to final GPE. We know the GPE equal to P into M minus GMM over R2 minus GMM over R2. R2 is the radius of the geostationary satellite's orbit minus GMM over R1. R1 is the initial radius, that is from the surface of planet. So R1 is the radius of the Earth. Okay, so that's going to be minus plus, so it's going to be GMM, we can take it out, 1 over R1 minus 1 over R2. So that's going to be GMM over R1 minus GMM over R2. I took GMM common. So 6.67 10 to the power minus 11. The mass of the Earth is given, capital M is the mass of the Earth, 6 into 10 to the power 24. M is the mass of the satellite, which is given as 650. Yeah, 1 over R1. So R1 is the radius of the Earth, initial radius. So that is going to be 6.4 10 to the power 6 minus R2 is the radius of the geostationary path, that is 4.2 10 to the power 7. Okay, that much of joules, that's the increase in GPE. So solve it. You will get 3.44 10 to the power 10 joules. That's the increase in GPE. Okay, so the rocket is launched from the surface of a planet. The following table gives the data for the speed of the rocket at two heights above the planet's surface after the rocket engine has been switched off. So at height h1, which is 19.9 10 to the power 6, speed is 5370 meter per second. At a height of 22.7, so it's moving away from the planet, the speed is decreasing. The radius of the planet is given, find the mass of the planet is the question. So here the satellite is moving away from the planet, so it's going and speed is decreasing, means the gravitational potential of the satellite is increasing. So gain in GPE equal to loss in kinetic energy. So we can say gain in GPE in gravitational potential energy equal to loss in kinetic energy. We are writing this for this, the satellite which is in motion. Gaining gravitational potential, final kinetic GP minus initial GP. So that is minus GMM over R2. The R2 is height h2 plus the radius of the planet h plus r plus h2, that is the radius of the orbit when it reaches the height h2, because all the distances should be measured from the center. So these are the heights above the surface of Earth. So minus gmm over r2 means r plus h2 minus gmm over r plus h1, that is equal to loss in kinetic energy half m initial kinetic energy V1 squared, that is given here, minus half m V2 squared. Okay, we'll substitute. Okay, so here minus into minus plus, so we'll write that one first. So Gm, the symbol m all will get cancelled. That is the mass of the satellite. So m, symbol m, these all m will get cancelled. They are the mass of the satellite. So Gm into minus into minus plus 1 over r plus h1 minus 1 over r plus h2 is going to be half V1 squared minus V2 squared. Okay, so we know everything except capital M. So G we know 6.67 10 to the power minus 11 into M 1 over R plus H1. So R is given as that is given as 6.38 10 to the power 6. H1 is 19.9 10 to the power 6. So we'll add it and put it. That is easy. So R plus H1 6.38 10 to the power 6 plus H1 19.9 10 to the power 6. If you add both, we will get 26.28. So that's easy rather than making too much of writing too much of numbers here. We'll find that first. That is 6.38 10 to the power 6 plus 19.9 10 to the power 6. That will be 26.28 10 to the power 6. That is R plus H1 minus 1 over R plus H2, that also 6.38 10 to the power 6 plus 22.7 into 10 to the power 6. Better do it separately and substitute. That will be 29.08. 29.08 into 10 to the power 6 equal half into V1 squared 5370 squared minus 5090 squared. Okay, so we know everything. All the numbers we know. Only thing solving is a bit careful. So you will get, when you solve the left side, you will get 2.44 10 to the power minus 19 m. If you solve everything, you will get this much. On the right side, when you solve this one, you will get 14.64 into 10 to the power 5. So find them. You will get 5.99 10 to the power 24. That is 6 into 10 to the power 24 kilograms. Okay, so third question, mass of a planet is m and its radius capital R. So this is like, this is the planet, its mass is m, this is radius A, this is the center, radius is R. A rocket is launched from the surface of planet such that rocket moves radially along it, so like this. Away from the planet. The rocket engines are stopped when the rocket is at a height of r above the surface. So r above the surface means from the center it's at a height of distance of 2r. So this is r. At that point the engines are switched off. then it's moving from R above the surface, height of R above the surface of the planet, so that the change in GPA of the rocket when it moves from height R to 2R. So it's moving from R to another point which is 2R. So that means we can say it's moving from X to Y. When it moves from X to Y, we need to get an expression, this one. Okay, so again it's not a big issue. So it's moving away, so it's losing gaining GPA. So gaining GPA, that is delta P equal final GP at point Y. So the radius, the distance from the center of the earth will be 2R plus R 3R minus GMM over 3R minus GMM over 2R. That's all, nothing, just solve it. So that's going to be minus into minus plus GMM over 2R minus GMM over 3R. LCM is 6R. So that's going to be 3GMM minus 2GMM. So that will be GMM over 6R. That's a change in or increase in gravitational potential energy. Okay, the same question, second part. When the rocket moves from the height R to 2R, its speed changes from 7,600 meter per second to 7,200. So it's gaining GP. So you can see the speed decreasing means it's losing the kinetic energy. We got an expression for the loss gaining GPs. We can write gaining GP, gravitational potential energy, equal to loss in kinetic energy. So gaining GP, we got the expression for that. Already we derived it. That is GMM over 6R equal to half M loss in kinetic energy. Initial kinetic energy at a height R, which is 7,600 squared minus 7,320 squared. Okay, so here M will get cancelled, and the radius of the planet is given 3.40 10 to the power 6, that is R. So we know everything, only thing we need to find the M. These two M, the mass of the satellite, the rocket will get cancelled. So we need to find the capital M. So M is equal to 6 times R, we cross multiply, 6 times R, that is okay, so I'll write the M subject here again. From this, M is equal to, when 6R goes here half, so that will become 3R into 7,600 square minus 7,320 square over divided by capital G. Okay, so we'll solve it. M is equal to 3R, so 3 into, the radius is given 3.40, 10 to the power 6, 7,600 squared minus 7,320 squared over G. The capital G, 6.67, 10 to the power minus 11. Okay, solve it, you will get the answer. So mass M equals 6.39, 10 to the power 23 kilograms. That's the mass of the planet. Okay, so the last topic is escape speed. Escape speed means speed at which an object is projected from the surface of a planet. So what's the minimum speed required to escape completely from the gravitational pull of the planet? So that means if it wants to completely escape from the gravitational pull, it should not experience any gravitational force when it reaches a point where that's the maximum distance from the point, that should be the infinite distance, because the gravitational force could exert up to infinite distance. So infinite distance means very large distance, yeah. So the object should be launched from the surface of a planet at a speed u. So the minimum speed is called escape speed, such that it never comes back when it is projected, not a rocket motion, just one throw. After that it should not come back. So it should reach an infinite point where just reaches, so minimum speed, so just reaches where its speed becomes equal to 0. So the radius of the planet, we take it as r. So the initial, when it moves from this point to this point, it's losing the kinetic energy and gaining gravitational potential energy. So loss in kinetic energy is equal to gaining gravitational potential energy. So at infinite distance, the gravitational potential energy is equal to 0 because it has reached infinite distance. GMMO R is infinity. Also, we are calculating the minimum speed. So minimum speed means it just reaches. So at this point, the kinetic energy also becomes equal to 0. Okay, so loss in kinetic energy equal gain in gravitational potential energy. So loss in kinetic energy means initially its kinetic energy half mu squared. We are finding the minimum kinetic energy such that it completely escapes from the gravitational effect of the planet, means it should reach the infinite distance, half mu squared. At infinite distance, the kinetic energy equal to 0, just reaches, so the speed becomes 0. Gain in gravitational potential energy, that means the final gravitational potential energy is 0 because at infinite distance it should reach, because otherwise there will be gravitational pull on it. So the final gravitational potential energy is 0 minus Gm m over r is the initial gravitational potential energy on the surface of the planet. So half mu squared is equal to Gm m over r. M get cancelled, so u squared equal to 2Gm, where m is the mass of the planet, 2Gm over r. So we can write this as 2Gm over r squared into r. R is the radius of the planet. Gm over r squared is the gravitational field strength. So that means u squared is equal to 2gr. So the minimum speed, what we found is the minimum speed, so that is the escape velocity. U escape is going to be square root of 2gr. G is the gravitational field strength on the surface of the planet. R is the radius of the planet. Okay, so that's all this gravitational field. I hope you understood. Okay, we'll meet during the next lesson. Bye.